hope you can hear me. Good. Well, we've just been hearing about some of the applications of twistor theory in high-energy physics. It's certainly an area that is starting to come into its own. Twistor theory for many years was not something which was paid much attention to by the physics community, although there were many areas of mathematics that seem to be influenced by differential geometry and representation theory in particular. Now, I've been concerned primarily with how general relativity fits into the twistor program. This again is part of the high-energy physics program, if you like, because they look at graviton scattering and so on. This is all a perturbative attitude to physics. I'm more concerned with trying to do something which is non-perturbative and which extends some of the more impressive features of twistor theory. I think it's still a big audience, so I know I shall have to be somewhat descriptive in what I say. I should also repeat what I said last time, just so that in case anybody was not here, or just to remind people the kind of thing that twistor theory is about. The basic twistor picture, we have a light ray. I'm sorry, does this work? We need to focus a bit better. I hope that screen can be seen. Don't worry. This was the slide I started with last time, so I shouldn't say too much about it. But the light rays are points from this space, and the points from this space are Riemann spheres in this space. The idea is to try and make this space, the twistor space, to be a complex manifold of some sort. And I'll start by introducing coordinates, and then we have to have this condition relation here, which is part of the definition of Pn. You restrict that condition relation. Don't insist on that condition relation in an extended region here with two arms of an objective, complex projective free space, which is divided in two by a real hypersurface. And the Riemann sphere over here is supposed to be a straight line, an complex analytic straight line in complex projective free space. And we've been saying C-norms before. Often one talks instead about the non-projective twistor space. Algebraically, that is what one finds is easiest to talk about. So you have points in this is now C4, a complex vector space of 4 dimensions, and the twistor proportionality is the point in the space here. And physically, one can interpret these things in terms of the momentum and the angular momentum of a massless particle. So that's sort of basic geometry in physics. A lot of what one does in this subject, unfortunately, I think for many people who are familiar with this notation, one uses twistor notation and focus on how's the focus? Anyway, I won't go into the notation particularly because it would take me too long to go through everything. But you have a translation between the vector and tensor notation by these small letters and capital letters for the twistor. And roughly speaking, the vector index corresponds to tensor product of a spinor index with a complex conjugate spinor index. The notation automatically accounts for that. And then you have a basic representation of these division matrices, and the metric itself becomes a product of this sort of skew-symmetrical form, two forms, if you like, in the spin space. And it's a geometrical interpretation showed you last time, which shows that a little more clearly. This will be important for some of the things I want to say, that you have an interpretation of a single index spinner and a twist spinner. Proportionality is just the direction on like curve, in other words, a point on the ring of sphere representing this point, the twistor space, and there's a tangent vector which corresponds to a flag plane. This is a two-dimensional plane which is tangent to a cone here, and we have freely rotating it, which corresponds to rotating this tangent vector here, and the spinner goes to minus itself to go once around, and back to plus itself again when we go twice around. So apart from the ambiguity of sign, this is a very direct and ambiguous representation of a two-component spinner. Okay, that's all very much background, which I said last time. What else do I want to say in connection with that? Let's put this over here. I think I will inform you this one last time too. So a twister, before I just used the extended coordinates, that they divide neatly up into two spinners, the pi and the omega. I should mention that those people who follow the high energy physics literature will usually find lambda and mu here, and the indices, the conventions are all upside down as far as I'm concerned. It started because they got their conventions from my original paper on twistor theory when I used lambda and mu. That's not the important thing. The important thing is that I had all my conventions wrong as far as I'm concerned. That's so I put the downstairs index upwards and the upstairs one downwards. And people often don't worry about that, but when you do conformal transformations, it's very important that this thing is a covector or co-twistor or co-spinner. The index is downstairs, and this index is upstairs, and this is related to a momentum. Momentum is a covector, and so when you multiply this by its complex conjugate, down here, you multiply this complex conjugate, you get a covector. That lower index of this covector, and that corresponds to the lower index here. And the upper index on the omega, because it's a dual thing, that's dual complex conjugate because it's no prime here, and dual because it's not upstairs. And this is very much reflected in what happens when you take a complex conjugate, because the complex conjugate of this reverses the two as well as taking complex conjugates. So pi becomes the first location, and omega in the second location, and this then becomes the dual of this. So z bar is this times this plus this times this, and that was the form I wrote last time at the bottom of the page, I think it was. Anyway, the notation takes care of a lot of things. When you move the origin, the pi's remain fixed there. Free vector, free space, right? They're independent of the choice of origin. But the omegas change with this explicit formula here. And this is all consistent with the interpretation of the momentum of the massless particle being pi times pi bar, the angular momentum being this formula here, a bit complicated, but basically it involves the symmetrized product of the omega and the pi, and that gives you the self-dual and anti-self-dual parts of the angular momentum 6 vector. So this is the physical interpretation of twistors directly in flat space. Now, last time I also mentioned the basic massless equations that one has. I've got 2 slides of this, I'm not sure which is the other one. Take this one. I think. Here we are. You have these equations, which are the massless equations. If they're prime indices, that's the right-handed part of the particle. So the particle whose spin is a massless particle, and this is the wave function of that massless particle. It has a right-handed and a left-handed part. The right-handed part is described by this symmetric 2s index. S is the velocity, so it's 2s is the number of indices here. That's an integer. S can be a half integer. And this symmetric object describes the velocity S particle, which is right-handed, since you don't have indices, it's the left-handed part. The equation is just the same, except that the indices are the other way around. You have the wave equation, it's spin 0, and then the twistor wave function is a holomorphic function of homogeneity degree as given in this thing here. It's minus 2s minus 2, so that you find for massless particles spin 1, say photon, so you've got plus 1 and minus 1 is the two values of s, and in the twistor description, you have either minus 4 homogeneity or 0 homogeneity for the twistor function. And for a linearized graviton, you would have spin 2, or helicity 2, or helicity minus 2. Helicity 2 gives you minus 6, and minus 2 gives you plus 2, which is very lopsided. It's not the lopsidedness is not important if you're working simply without worrying about interactions. It is important when you're worrying about interactions. And I'll say a bit more about that. You can take the dual description, and of course they're all the other way around. So it's saying that now the complex conjugate, so the numbers are reversed. And the way that one represents the wave function of the twistor, these are the wave functions here, in terms of the homomorphic function, is given by these contour integrals, which I did show you before. If it's for s equals 0, then you just do a contour integral with here's this epsilon again, so it's a one form that I've got here, and we integrate that one form around a loop, and this you can see in the projective space, so you have here is projective twistor space. The point here, that's a point in complexified space-time. It's complexified space-time, but we will often be interested for a wave function that should be in a sort of forward tube. That's where the position vector has an imaginary part which points into the past. That is the past in the interior of the past light cone. And if your wave function extends into that region, which is called forward tube, then it's automatically a positive frequency. And wave functions for free particles should be positive frequency. And what this means in twistor space is that this line, which are in the forward tube, this line lies in the top half. So that corresponds completely to the point being, I had a picture there somewhere, I'm not sure I can see it where it is anyway. It corresponds to the imaginary part of the complex vector x being pointing into the past. So that's the forward tube. And if your wave function extends holomorphically into that region, that's where the x now is in the top half of twistor space, that will be a positive frequency wave function, as it should be, propagates into the future. Now, twistor theory nicely accommodates that. If you say, well, we're looking at the top half of twistor space, I should say there's a confusion which may worry people, that I said the top half of twistor space corresponded to right-handed spinning and the bottom half left-handed spinning, and I'm saying something completely different, that the top half corresponds to positive frequency and the bottom half to negative frequency. That association is entirely coming about because I'm looking at the twistor description and not the dual twistor description. So you stop worrying about that, is what I'm trying to say. It looks like a lopsidedness. It is a lopsidedness, but that comes about from the fact that I'm looking at the twistor description and not the dual twistor description. Okay, now the top half corresponds in this picture to positive frequency. The bottom half would be negative frequency. Now, the singularities of the twistor function, that you have to have singularities in the top half, because otherwise you wouldn't have any answer to your contour integral. But this example here is very good for showing you what happens. You've got two planes which are singular, and this gives you 2 points of intersection with this line, and they'll contour. For each value of x, you have a Riemann sphere, and then you integrate around that Riemann sphere, and that gives you the value of field. If you have indices on it, you put a lot of pi's in for the right-handed, or rather d by d omegas for the left-handed. There's a point I want to make here, which is interesting. I haven't said really anything, I mean, apart from saying positive frequency, anything which is specifically quantum mechanical. But nevertheless, one sees the relationship between the complex conjugation and going over to the derivatives. So it's the Twistor commutation rule, which comes about from us attempt to make Twistor theory into a quantum theory, a single quantized theory, first quantized theory, if you like, and that means that the pi bars. You say, what's the complex conjugate equation here? We put pi bars in here, but that's no good because those are homomorphic. You want the complex analytic integral here. So you put the pi bars, replace them by d by the omegas, and then you have the answer. It's curious because I had this formula here. It was really Len Houston who noticed that you could use these equations here, and then I realized afterwards that that's just this Twistor quantization procedure, but it's in a purely classical context. But I think it's important to point it out that you see this relationship between pi bar and d by the omega, which is the Twistor commutation rule, really, already appearing at this level. Okay, now, as I said before, these contour intervals, I mean, this is very special. There are singularities in some places, and they would spoil the Lorentz invariance in one picture, because suppose you rotated, then these planes would go somewhere else, and you couldn't add one where the planes in one place or where the planes in another place. Well, maybe you could do that, but you start smearing by adding loads and loads of them. You have big regions here, and then you rotate them, and they don't add up very well. So it's a nice feature of it, but this is really doing first homology, and we are now looking at a particular case where you have a covering of your top half of Twistor space, which has one region leaves out that camel hump, and the other region leaves out that camel hump. The Twistor function is on the intersection of those regions, which is where the camel humps are not, and the region that you're interested in, the whole part of BT plus, is the union of those two regions. And this is, if you have more and more added together lots and lots of these things, it would make a great mess. But the understanding of that mess is in terms of Twistor cohomology. You could add lots of them together as long as you keep taking common refinements of your coverings, and then you get more and more sets here. But the important point is to extract the notion which this is trying to tell you. And if you have many sets, you can say your Twistor function is really a collection of functions indexed in terms of the intersections of these U's. Because the U's here are open sets on the top half of Twistor space, and the Twistor function is really a collection of Twistor functions, each one defined on the overlaps between two of the U's, and these can be assigned, we call it Fij. It has to be antisymmetric because you're really doing a bit of a contour interval which goes in one direction, and then if you replace it the other way around, interchange these two, then it's the other direction. So you use antisymmetry, and then you need this triple rule here, because that means that if you move this point around within the triple intersection, it should change the answer, and that is the case with this cycle. The cycle rule holds, and this then forms a check cocycle, and you find that there are certain things that will give you zero if the Fij's are sums of functions which you found in one set or the other. So if your Fij here was a sum of the function on here and the function on there, or a difference, these h's, then it would give you zero. And so you factor out by all these things. So you take the f's modular distance here, and that's your representative of cohomology, and you end up with an element of first cohomology, this being the homogeneity degree of the function we're talking about is minus 2s minus 2, where s is the helicity of the field we're talking about. So that's one of the things I was saying yesterday, but I just thought I'd say a little bit more and keep you here. And the early motivation, one of the very strong motivations I had originally for Twistor theory was the analog of what you have with the Riemann sphere. And with quantum field theory, you want to split your functions into positive and negative frequency parts. And the easiest way of doing this, rather than doing a Fourier analysis, which is initially what physicists were thinking in terms of, that you can do it more in mathematical, geometrical terms by thinking your function is defined as an equator here, and the positive frequency and negative frequency parts. So you extend it holomorphically into the top half. Part of it goes holomorphically into the top half, the other part holomorphically into the bottom half, and this is the splitting of the thing into positive and negative frequencies. I think the convention is usually this is negative frequency, that's positive frequency. We have something very analogous in our twistor theory, and it took a long time, although this was a big motivation early on, to find an analog of this for the full four-dimensional space-time, and that's what twistor theory does for you. How it did this was mysterious until we realized we were doing cohomology. So you say, yes, it's the same thing, but now your cohomology either extends into first cohomology, either extends into the top or the bottom, and you split your function into those two parts. And it is the same thing as we did before. Here it was just functions, and here it's first cohomology. So as I say, this finally realized one of the very early motivations behind twistor theory. Okay, now this is all linear, massless fields. We're not doing any interactions. It's just the free fields. And it's very neat, and it encompasses so many different things one wants for the wave function, and it also gets rid of all the field equations. That's all homomorphicity, and it's always seems to me that's really very attractive. Now, it does more. And what I want to tell you here is what it does more. And I have pictured here two constructions. I want to say, what I want to talk about mainly is the gravity one, which is the second construction here. But I came up with this, and I guess it's 1976 according to this slide here. And I think it was the next year when Richard Ward saw how to do it for gauge fields. So it was the same general ideas here, but he showed that you could have an instruction similar to what I was doing in the gravitational case, which I'll talk to you about in a moment. Here I'm just showing you a picture. The picture is basically, okay, you've got a first cohomology element, which is painted onto the space, onto the overlaps between different patches, and then you let the paint dry, and it actually slides the patches, crinkles the patches up there, sliding one across over another in a way which is defined by the element, the complex function which is on the intersection. I'll say more about that in a minute, but you actually do now create a deformed space by letting this originally passive function painted on the space to become something active, which deforms the space. And what Richard Ward did was to see how to treat gauge fields this way. So first of all, he did for the gauge field of electromagnetism, and then very quickly, he was only in his second year as a research graduate student, and so it was pretty impressive. But he saw how to do this for general groups, so this can be gauge groups which are very broad in what you're interested in here. Started off with U1, but then you can do SU2 or SU3 or whatever you want. Non-linear, normally non-linear gauge group. And then you are looking at patches here, which are have values in the linear group, or you construct a bundle. And this bundle now contains, I won't go into the details of it, but it does give you, when you translate back, you see that it gives you solutions of the Yang-Mills equations very generally, except that they're all self-dual. So when I say self-dual for Yang-Mills, well, let me see what it means for electromagnetic theory. You see the photons.
Just a second.
I'm sorry?
In those pictures,
yes.
Here you have three little things, and here you have four little things.
Three or four little things.
In the Kirk Medical, 1976.
I mean, the number of sets is just chosen randomly.
Yeah, I know. But you have four. Is there a reason for these four?
You sets here. Oh no, that's just an example.
Yeah. What important is it?
No, they would be 179.
My question is whether you only go to triple intersections, you don't go to...
Oh, you mean the triple intersections? Is that what you mean?
Yeah. I understand.
Yeah, no, it's only representative. You do what I said algebraically really before. The picture, I agree, you have to take with a certain amount of salt. But the algebraically, you have things defined on the intersections. You might have redundancies if you've got 4 of them, and so on. But the indices take care of what you should be doing. Yeah, right. But that, I've only used 4 sets here for descriptive purposes. It doesn't mean too much. But there are 4 other pictures, I think. No, you're right, there are only 3. Sorry, but that's irrelevant. But, yeah. But anyway, you construct a number this way, and although I'm not going to tell you how it works, it's very natural. You get the Yang-Mills connection, and that gives you a connection which is anti-self-dual with the conventions I'm using here, which means that the curvature, which would be one of these things here, would be 2 indices on the spinners, and then other indices for the gauge field. But the point is, it's this one and not this one. In other words, you're looking at the anti-self-dual gauge fields. And that had quite a big influence in pure mathematics, because it relates to all sorts of integral systems, and a whole lot of work was done on integral systems. There are papers written by all sorts of very distinguished people on this kind of work. And it's a big subject. And there's a book by Mason and Woodhouse which discusses all these things. And I think, I'm not going to talk about it here, but the reason I'm going to talk about it here, primarily apart from being largely ignorant about any of these things, is that that's all within the anti-self-dual picture, where things are in a certain sense more integral than they are, in a certain sense they are integral. And that applies both to gravity and to electromagnetism or the Yang-Mills fields. So you have something which works in the anti-self-dual case, or self-dual if you simply reverse the formalism, but that's not very important because we need to do both parts at once. Let me show you the gravitational case, and that's really what I want to talk about. I should put this over here just to see the Now, the gravitational case, which was the first one, and this is the one I understand the best. Going back to this picture here at the bottom, you want a way, first of all, of converting your function, which in this case will be anti-self-dual, so we're looking at functions which are homogeneous degree 2. Homogeneous degree 2. And that function will give you a vector field, and that vector field will tell you how to infinitesimate these, how to form this patch. And then you have a triple overlap issue. It's easiest if you just talk about 2 patches, actually, so it's even going more simply than if you're asking about. So let me do it a little bit more explicitly. Yeah, I'll do it here. Okay, let's imagine that we have a piece of complex projected 3 space, which is a tubular neighborhood of a complex projected line. It needn't be for the most general constructions, but this is the sort of piece, the smallest piece that you work with. So we take a little tubular neighborhood. This is CP3 over here. There is a line in CP3, and just flatten that out to be a tubular neighborhood of that line. Now, this is going this way, we have a 2-sphere, topologically. That 2-sphere, I can imagine as broken into 2 hemispheres with overlap, and that's, in this picture, what's going on. So this is one hemisphere over here, that's the other hemisphere, and this is the overlap between the 2. On that overlap region, I shift the piece of projected 3 space. So it looks like this picture here. It's a bit of a mess, but don't worry too much. I'm not worried about the edges here. But what I am worried about is the fact that this complex projected line doesn't meet any point. It's not a whole curve. Now you have to appeal to theorems to see whether you can do this, and there within some open region, then you can find a new holomorphic curve which threads through here. Not this broken one here, but the actual genuine holomorphic curve. So it's a CP1, it's a Riemann sphere again, and we use the Codaro theorem to say that you have that, and I think Codaro extends arguments to say that not only can you do it, but there will be a 4-parameter family of these, as long as the deformation is within some open region, there will be a 4-parameter family of these holomorphic curves. They have to be ones which belong to the same homology class as the one we started with. You could have started here with a cube or something. So it's got to be starting with the homology class of a line, and then well, you can just imagine this continuous deformation. Then this line will be right on the homology class, and you then look for holomorphic curves, which are human spheres in the right homology class, and the 4-parameter family. Since it's a 4-parameter family, it would make a space whose points are these curves. And that space would be a 4-dimensional complex manifold. So you would call it 4-dimensional complex manifold. Now I'm going back to things which I said earlier, about quickly in my previous talk, that you have recognize the conformal structure of Minkowski space, that is flat Lorentzian 4 space, and then you complexify with this picture. Then you have when you 2 points in this Minkowski space, when are they null separate? When is there a null line through the 2 of them, null separated? That corresponds to these projected lines at CP3 intersecting. So they have an intersection, this point of intersection corresponds to the line that was real Minkowski space to begin with. And these things represented by points specified Minkowski space. So by simply knowing CP3 and knowing the lines in CP3 and knowing when they meet, you can reconstruct the complexified Minkowski space, which really is the Klein representation, which I was before. So let's put Klein representation here. And the points now correspond to alpha planes. So alpha planes over here actually correspond to points here. Beta planes correspond to lines. So that is the sort of canonical picture, which is the Klein representation. But when we deform, you still have a notion of these things meeting. And so therefore you still have a notion of null separation in this green space here. And you find, in fact, this is a general anti-self-dual complex space-time. Anti-self-dual, that means that the Weil tensor is anti-self-dual. The Weil curvature tensor, conformal curvature tensor, has this anti-self-dual character. And that you can see it's a general construction because you go backwards. Because when you have a Weil curvature which is anti-self-dual, then you do have, in the general case, alpha planes. Alpha planes are anti-self-dual null planes. What's a self-dual? Excuse me. Anyway, the one or the other. And they are the points that you get here. And then you have the other way around using beta planes. Now, in this construction, you retain the alpha planes, but you lose the beta planes. So you have conformal curvature in general, which shows itself up in the absence of beta planes. But the conformal curvature is necessarily anti-self-dual. I guess these are self-dual planes, isn't it? The conformal curvature is anti-self-dual, so that ruins the beta planes. The beta planes being the anti-self ones. But the alpha planes are still there. It's a completely general construction. Locally it is. So you can take any anti-self-dual space over here instead of the Klein quadric, and then you have the alpha planes in it. The alpha planes can be the twistor space, so you go that way. You go in the other direction. If you've got the deformed twistor space, which is this thing here, then you can reconstruct the anti-self-dual space-time. So space-time. Now, this doesn't have a metric in this sense. If you want the metric, the way I was doing migration here. There's a projection down from the twistor space down to a CP1. And you can see that's in the omega pi notation that I had before. It means you've got pi splits and they're globally defined. The omegas are more complicated, but you have a pi split that's globally defined. Now, you can actually slightly generalize this. Before, let me have this picture in a different form here. This is just what I was doing before, except I'm doing it infinitesimally. Infinitesimally, it should be the spin 2 case, which I showed here. That's the spin 2 case. Or minus 2 case. This is the minus 2, which is the case at the bottom down here. In that case, is where you have a twistor function which has homogeneity plus 2. And now what you do, for the infinitesimal deformation, you take d by dz of f, dz are the twistor coordinates, and then you take the infinity twistor, plug that in, and this gives you a vector field. And that vector field gives you the actual deformation here. And then if you could exponentiate that, then you would get the finite deformation, which I was telling you before. But infinitesimally, it ties in exactly with what we had in the previous contour integral construction. It's exactly what you get here with the f thing in that other picture being this homogeneity 2 function that you have in this table. Okay, so that's the nonlinear graviton construction. You have to go through it and see, okay, it does give you get a connection, that connection is zero torsion, and so on and so forth. It really works. I should say that there was a generalization of this that Richard Ward did. I had some initial ideas that he made into a theory. Well, yes, it does. You see, another way of... I've written this with the infinity twistor. Now that infinity twistor is degenerate in the case of zero cosmological constant, is what I'm doing here. And that gives you the projection, which I was talking about here. But if you take the cosmological constant is non-zero, and just to remind you of all the stuff I was telling you previously, that we had in the flat case, the Klein picture, if you want to give it a metric to the space here, introduce the infinity twistor, or the metric twistor, you might call it, which is a symmetrical object. My microphone, come back again. The symmetrical object, which is an infinity twistor, which gives you the metric, and it also reduces the conformal group down to the Poincare group. And this is the thing I alpha beta, which for zero cosmological constant, which is what you want when you're talking about well, Minkowski space, of course, the zero cosmological constant, then you have a degenerate infinity twistor. And that is what gives you the projections here. But in general, if you have a non-degenerate infinity twistor, then you have this infinity twistor, which is you can't see all these pictures at once. For the center space, it's positive, this factor, and in the center space, it's negative. And that corresponds to this infinity being a non-singular rather than a curve. I just wanted to say all that because Richard Ward then carried this out in the case of a non-degenerate I-alpha. The construction is exactly the same, except you don't have this projection. You have a two-form in space here, which is not degenerate. Let me not go into details because that's not too important for the moment. But I just want to mention that yes, the construction does work. Also, in the case of, now I realise I forgot to say, what I should have said is that this construction not only gives you a metric in the case of the degenerate I-alpha beta, but that metric automatically satisfies the Einstein equations. So you have Ricci flat the richer tensor vanishes. Now, if we introduce the more general construction of the Richard one, where this I is now non-degenerate, the whole thing goes through just as before, except that now you have solved the Einstein equations again, but this is now an Einstein space in the mathematician sense. That is to say, you have the metric and the Ricci tensor are proportional. And in fact, proportionality is this lambda, the cosmological constant. So just put that in to show that it's a bit more general than what I was saying before. That it's just, it works just as well. You don't have this really clean projection, but it works just as well. You have a way of getting, at least locally, all the left-handed or anti-self-dual, that's to say, the vital curvature, the self-dual part of it vanishes, but then it's all solutions of the Einstein equations, with or without cosmological constant, but vacuum all those by this construction. Now, get is rather that's a word which is a little bit too strong here. They're all implicitly there, but if you want to write them down, it's not so easy. You can write down these definitions, that's easy. You can just take a twistor space and slide it along, glue it down, you've got a new twistor space. But what is the space-time? You want to find that space-time, you've got to find where these orthogonal curves are. And that is non-trivial. You could do it in often many special cases, but the general problem of finding those lines is a non-trivial problem. It contains the solution in principle, but it need not be a very practical way of finding the solution. Now, the big problem here, of course, is the fact that we are stuck with anti-self-dual solutions. And this is what I call the googly problem. You might say, what's googly? This is a terminology that is probably only familiar to people who belong to the former British Empire, because it has to do with cricket. And it's the name of a ball which is bowled by the bowler. See, people say, oh, that's essentially a screwball in baseball. No, it's not. You see, cricket has the characteristic feature that the ball bounces, and therefore it's sensitive to whether the ball is spinning right-handed or left-handed about this direction of motion. And physical masses particles do that. A photon, its spin is about its direction of motion, either right-handed or left-handed, are the two felicities. Now, baseball doesn't do anything for it, but in cricket, since the ball bounces, it does. And so, a googly is a ball which is bowled with a very clever way. See, normally there's a thing called a leg break, which spins left-handed. And there are some bowlers who do this very well. But the real skill is if you can look as though you're doing that, but very subtly, you hold your hand in a very clever way, I don't know how they do it, and the ball spins the other way. So it gives you a right-handed spin within the general framework of left-handed spins. And that's a googly. It's also very difficult to do, and that also is a broken material, because this is pretty difficult too. But it has been, in my view, the major stumbling block in twistor theory for, I don't know, 40 years, 50, I can't even remember now, a long time. And when I say the major stumbling block, it's not just for general relativity. You see, the Yang Mills also started in this. You simply have the left-handed solutions in this construction, you don't have the right-handed ones. So this is the thing. I said, you want to have a way of using the same framework as we had for the left-handed ones, but which usually the right-handed ones is also. So a solution to the googly problem has to be the major stumbling block in the development of twistor theory. So what's palatial twistors? Well, this is a proposal, and it's still only a proposal because I don't really know whether it works or not, to generalize the framework that we had before to the ambidextrous, or whatever you say. If you like, the same arm that was likely to spin both ways. Now, a suggestion, I was thinking about this idea, I shouldn't have to say the name, or I'm slightly embarrassed by that. It's a discussion I had with my peer, who I was suggesting some ideas, I didn't see how this would work, and he said, oh, well, you've use it non-chronically. That was really the gist of the argument, and this happened to be in the Paris at the time. That's why it's called it. I think I can call it palatial for a different reason now, because we I hope, in this subject, so we can say that the past refers to that time. Anyway, that's Palatial Twistor theory. In order to describe general Lorentzian, globally hyperbolic, well, that just means that we don't behave too badly globally. Space-times, in twistor terms, we appear to be driven to non-commutative twistor geometry, even for classical space-time. See, this is a very quantum idea, and the idea would be to try and drive the thing in the direction of quantum gravity or something. But the things I'm going to say today, except just at the end of my time, will be entirely classical space-time geometry, but doing it in a quantum way. So it's kind of a quantum approach to classical space-time geometry. And I will have a picture, something like the one that I was showing you before, with a twistor space, crucially a non-projective twistor space. Keep track of the scale factors, but that's this picture I have here in some sense, but where there's another kind of non-commutative picture. And this is work in progress very much. I just want to give you a hint. What is the time? How long have we got? Negative time, probably. Well, it's just as well I don't have too much time, because I don't altogether know what I'm talking about. It does seem to me that it's where we have to go. And there are a lot of things in the talks we had with Ernesto just recently, which made it look very intriguing. The geometrical structures that come out naturally in twistor theory and those which come out in non-constant geometry are so much related to each other that it's really very, very tempting. But let me try and say a little bit more completely what we're going to do here. Just to remind you, we have the seemingly harmless-looking commutation rules, which come in now and again when we're trying to do things which may have a little bit to do with quantum mechanics, but pretty classical things nevertheless. And you have the commuting, the Z's commute with themselves, Z bars commute with themselves, but Z bar have a canonical commutation rule. And if you remember, thinking about this was very crucial to leading one to homomorphic functions as your wave functions, because to say you want a wave function in ordinary standard physics, usually got momentum and position, you choose one or the other, either momentum description or position description. These are canonical conjugates, and one becomes the derivative with respect to the other. Now, you have to choose what you're doing, and here I'm choosing what you're doing, maybe it's the twistor description, and then the Z bars become derivatives with respect to Z's. And so but that would drive you to thinking in terms of homomorphic functions as your wave functions. And so that was part of that already. Okay, so what we're going to do is to take these rules and somehow think of them as done in a patch. So we have something like a construction we had before, which was before we glued together. Let's just do two patches, not lots of patches, but just two patches, and you glue them together, and you want to glue them. You see, the thing I was asking my criteria was something which didn't seem to work, but I didn't know what to do. Namely, you want to have no space down here. Somehow you've got the sheaf of holomorphic functions sitting up here, and you try to patch something together where there isn't a space down here. And I couldn't see how you do that, but then you said, well, what about non-commutative geometry? You see, wow, yes, that seems to be a good idea. And I always steered away from this. It seems something that I never could understand. Never tried very hard to understand, and I realize I do have to try much harder to understand it. So you basically have now the algebra of the, you don't have a sheaf of holomorphic functions over a given space. You have the algebra of the z's up here. So you've got sort of Heisenberg type algebra. We did not much z's, but debugging z's. Let me mention the point here, you see. One of the driving forces, of course, behind twistor theory is holomorphicity. You want the power of complex analysis to be what carries you forward. Now, as soon as you introduce complex conjugates, well, you're in trouble. And any sort of natural thing, obvious geometrical thing you do in spaces and so on, immediately brings in complex conjugates. So the philosophy here is okay, once you see a complex number grid, you quantize. And that's the basic rule here. So it's okay, I'm not going to do something non-homomorphic. That would be travesty, that would be heresy, I should say. Heresy in this view. The dogma is you can keep homomorphic. So you say, okay, you can keep homomorphic if you make partial derivatives with respect to your variables instead. So if you look at the algebra over here, now you see, in quantum mechanics, it's the sort of thing physicists do. When you've got this algebra of operators, you look for a complete set of commuting operators. And then the rest of the algebra comes from derivatives with respect to those. And that's a very standard quantum mechanical thing. So now I'm saying, find a complete set of commuting operators for your algebra. And here, on the other patch, it's got its algebra, and you might not find a set of commuting operators which matches the ones over here. But you don't care about that now, because you say, well, you're going to match the algebras, that's all. I'm not going to match the manifolds, which I'll give you the complete set of commuting operators. But I'm saying, no, it's the algebra which I'm carrying across from my side to the other. So it's a picture, something like that. Okay, now, I haven't really going to tell you there's a lot of things which come into this picture. How they all tie up together is not yet completely clear, but I think I should mention all sorts of different things which come in and are clearly relevant. First of all, let me mention the fact that this Roland, a lot of things I've been saying up to this point anyway, the fact that if you take the light ray space, you see in this crystal picture, you've already got the light ray space. That's just going back to my previous picture. You've certainly got the space of light rays, and that's the Pn. The problem here is to try and extend it here. Now, if it's a conformally flat space here, then you can extend this as a complex manifold. If it's conformally curved, then it looks as though this extension is a non-commutative space. Now, this is what's new in this approach, in the Palatial Twistor approach. And that's what this other picture is trying to do. But nevertheless, you still imagine that if you're looking at a Lorentzian space-time, you've still got light rays. So those light rays, in other words, this space here, are geometrically clear-cut, and they are there. Okay. Now that light ray space is naturally a symplectic manifold. Let me qualify that a little bit. If you have a light ray space, which would have been the Pn thing, then to make it a symplectic manifold, you need the momentum scaling of the light rays. So each light ray isn't just a trajectory of the photon. That photon, and when I say photon, it just means a massless particle. It's not an actual photon. That photon has a frequency, and that frequency is a momentum attached to it. So you have a null vector, that was the p or the pi, if you like, when you square it. That null vector gives you scaling to the light ray. And given that scaling, you have a symplectic manifold. And here you can find this thing without twistors, if you like. It's just PDXs and so on. It's a natural symplectic structure that space has. That's fine, that's there. Now, what else do we have? Well, what you can do, is what you can do here, is you can take that symplectic manifold, this light rays here, this is the space of those light rays, and you try and do geometric quantization. Once you've got a symplectic manifold, this procedure of geometric quantization is a natural thing to try and do. It's a bit floppy, there's a lot of freedom in it, in a certain way. But nevertheless, it's a natural thing to do. Now, what is the key thing in geometric quantization? Well, the first step you do, what I'm talking about, I suppose, is technically pre-quantization. But the first thing you do is to take a circle bundle. So this is your symplectic manifold. This is not going to be a curved space-time, Lorentzian. Okay, it's globally hyperbolic, but that's a mild restriction to our purposes here, not a local one anyway. This space here has light rays in it. The light rays are given by point. It can be momentum scale light rays. That gives you point in this symplectic manifold. First step, construct a circle bundle over this space here. What's that circle bundle? Here it's given to you. This is a very specific thing to the number of dimensions we're working in. The symplectic manifold comes about if you have a 73-dimensional space and construct the light and do exactly the same thing in the symplectic manifold. But you're not given a circle bundle. Here, the circle bundle is there. It's there because you can take a spinner pointing along the light ray, and that spinner is related to the momentum through pi bar equals p. That's the formula we had before. The p is momentum, in other words, the momentum attached to that photon is the pi spinner times its complex conjugate. But what you lose in multiplying the pi spinner by its complex conjugate is the space factor. That space factor is a little flag, remember that? And that little flag rotates round the light ray. This will work in other dimensions, it only works in this number of dimensions. But that gives you a circle bundle, which is just sitting there. And then you say, for pre-quantization, you construct a connection in this over here, with values in the circle bundle here, and that connection has to have as its curvature the symplectic two-forms. And that's the thing I've got written down here. And lo and behold, in fact, do a little bit of geometry and then we'll go through it. You can see that that symplectic connection is geometrically defined, the whole thing. It's there, canonical, in this whole picture. The fact that it's canonical is in some sense bad news. Well, no, I'm not sure about that. It's canonical, but it's floppy. That is to say, you can do it in a sense in different ways. I don't know how the language works here, but you might say canonical when it's given to you. But nevertheless, you can do it in ways where you patch together the fusing in this connection is important. I think it's more when you extend away from the light ray space and when you're trying to make the twisted space. You see one or the other, but that's where your freedom comes in. And a lot of things I'm saying are vague because I'm not absolutely sure of the direction we should go. One thing that I'm sure is important is this notion of local twistor transport. Now what's that? This has been hanging around for a long time, and we've known about it, and it's an example of Carteles connection and all sorts of things. It's a natural thing in twistor theory when you do have a curved space-time, and this we've known about for a long time. Suppose you have a conformal Lorentzian four-dimensional manifold, such as our space-time that we described here, and you want a connection on what we call local twistors. Now, it's only applied as before, but they're only defined at a point. They agree with what we had before, except that they're local. That is to say, what we had before with the omega, if you remember this, was something like the moment, you have a light ray out here and an origin here. The omega has to know how far away the light ray is. It's kind of the moment of that light ray about this point. So it's a moment thing. Now, as you move along the light ray, that omega remains fixed along the light ray, but it's defined only with respect to the origin. If you move the origin to the light ray, then the omega will go to 0. So if origin is on the light ray, omega is 0. But it has to know where the origin is in order to know what this thing is here. But the point of view is a bit different. You say, each point you have an omega and pi, and you have a way of transporting around. So you can take a curve in your space-time, take your omega and pi around, and when you have a light ray, which it's supposed to describe, sorry, it doesn't actually, let me say it again. If you have a light ray, then omega is 0 all the way along the light ray. Whereas if you have a general omega and pi, or a general light ray sitting somewhere else, I suppose we did it in flat space. If we did it in flat space, you would certainly have these omegas and pi's the same as we had before, but they are omegas and pi's as though the origin is the point you're looking at. So if you take some random point, you say, okay, what is the twist? How is that twist theory described? Well, it's omega and pi, but if the origin had happened to be at that point, then omega would have been called. I hope that's reasonably clear. I don't know if I said it very well. But you need now to know what happens as you walk along the curve. And as you walk along the curve, we have this propagation equation. The derivative t is the tangent vector of the curve, and it tells you what omega does as you go along the curve. This tells you what pi does as you go along the curve. If it was flat space, this thing p would be 0. P is basically the Ritchie tensor, but with a slight change in its trace. It's an interesting, useful thing that you have in form structure. It's the Ritchie tensor with the 12th of it times the it's minus half the Ritchie tensor, depending on the dimension, with a minus 12 of the trace taken out. And it's a nice conform one. Now the thing is that this propagation then does depend on the curvature in space-time. If it's conformally flat, this is integral, that is to say, take a loop, small loop, say, not infinitesimal, one which is contractible. As you go around that loop, you always get back to where you started. If it's conform curvature there, you go around the loop and you get something else. However, there's a very interesting thing here, which I knew for a long time and never quite saw the point of it, which is that if your infinity twister, well, your infinity twister to be constant is a necessary and sufficient condition for the Einstein vacuum equations. So the Einstein vacuum equations are equivalent to the infinity twister defined as I gave you before. Well, did I give it to you? Anyways, the infinity twister in the flat space case, where you now allow to define it in your local twistor space, and as you move around, that local twistor space might rotate around because of the presence of conformal curvature, but the infinity twister is constant if and only if the Einstein vacuum equations hold. Now this is something we've all been wondered about for a long time, you see. The Weyl curvature is something which tells you something is integral. It tells you that your space-time, if you conform factors, well, it's a conformal space, so if the Weyl curvature vanishes, it tells you integrably give a metric to the whole thing, which is conformally, I said that right. It tells you conformally flat, which is an integral thing. Whereas the strength of the Ritchie tensor vanishes, or is multiple of the curvature, didn't seem to be an integral thing. It's not the same sort of thing. Weyl curvature is telling you something integrates, whereas the Ritchie curvature doesn't. But look here, it does, you see. It tells you that the infinity twister is integral over the whole space. So I'd known that, but I couldn't see what on earth it was good for. What it's good for is what I'm trying to say now. I probably haven't got much time now. I haven't. Good.
Time for questions.
Sorry?
Time for questions.
Well, can I just finish my sentence? Finishing the sentence is to say that you see, what we want is an idea of a non-commutative geometry, which in some local sense is the same as you get in Minkowski space when you introduce this z bar versus d by z. So you have this quantum algebra defined in Minkowski space, there's no doubt about that. That non-commutative algebra gives you, in a sense, a rather basic type of non-commutative geometry. Now that non-commutative geometry should be locally definable in the curve case, and in patching things together, it gives you a local, a global character. Then from that, you can go back and extract the space-time. And that seems to be a perfectly good thing to do. It requires more understanding about what this twistor space looks like. The point which I only realized fairly recently, just the other day, in fact, maybe even this morning, is this picture which I showed you before, this is the S1 bundle over S2, which is given by different parallels of vibration of S3. You also naturally have another circle, that is to say phase, because the twister that this represents a twister which is non-null. The twister that represents has the P has a phase in it. So you have a circle sitting there, which is completely global to this thing. So the structure, if you want the twister, now this is a twister really which is not on P again. So if you're talking about flat twistor space, we're talking about the twistor which is not on the space Pn which represents light rays. We're looking at a non-null twistor. And these non-null twistors are defined in the flat twistor space by this picture. Now this picture, if you want that twistor also to have its phase noticed, that's an additional circle. Now, the picture of the additional circle is a space that Ernesto was telling me is essentially the fundamental model for a non-constant geometry. Now, I didn't know anything about that before, but this seems to be incredibly suggestive. That this non-constant geometry is sort of hiding in this picture together with the extra phase that you automatically have because it's twistor theory. So twistor theory is just sitting there waiting to have this non-constant structure that Ernesto is telling me how to detain. Okay, but that's all I want to say, I think, about the things. I just want to say one more thing, which is more speculative than what I'm saying now. You're saying a bit speculative, but I'm coming to think of it. It really should work, particularly this thing at the time between this very natural thing coming out of twistor theory and the non-constant geometries that are already known. The other thing I did like to say is the final something, is I want to be a little bit crazy too. You see, we here have had a conversation between Cinvestav. Very early in twistor theory, I did wonder about whether the Z should have a commutation rule, or the Cinvestav as well. And I went home and then fiddled with it for a bit, and I realized at that time, thinking, no, it was a cosmological constant, and my eyes were degenerate. And I fiddled around, and I saw you could get rid of it, and it was back to the commutation. It didn't do anything, you were back to here. However, if you have an eye which has a cosmological constant, non-degenerate, I don't think that works. So I think you now have these three commutation rules all intertwined with each other. Now, if you didn't have these ones, it would certainly not be anything about quantum gravity. It would not be quantum gravity. Why would it not be quantum gravity? Because quantum gravity requires the Planck length to be fundamental. This is what defines the scale of gravitational quantum effects and so on. The Planck length is 10 to the minus 33 centimeters, which is ridiculously tiny. It's 10 to the 20, smaller than any ordinary self-respecting particle. So you're looking at ridiculously tiny scales, and people can say, what the hell is it? But it has importance in various things where quantum mechanics and space-time curvature we're having to relate to. If you don't have any room for that Planck length, you can't have a quantum gravity theory. So what I was telling you up to this point, if it's anything in physics, it's classical general relativity. You're describing classical space-times. You're not talking about quantum space-time. If you wanted to go further than that and talk about quantum gravity, you could put that information in here. This is some new constant, or the constant will be related to random and all sorts of things, which could encode the Planck scale. And it would have to encode a huge number as well, because the Planck scale is very, very tiny things, the cosmological constants do very large things. There is an enormous number going from one scale to the other. So hiding in physics, there is this enormous number that's been known for a long time. It's a big mystery why gravitation should be so weak in comparison with other forces. There is a huge number. So there has to be a huge number hiding in this. I think there is. It needs to be looking a little carefully at the dimensions of things. The epsilon and the lambda interrelate in some such way. I'll just leave you with that speculation at the moment. Thank you very much. I mean, just to actually say that the notation, although the high-end physics people don't use it, they use but I use it very specifically because in physics one uses p for momentum, and the pi is the square root of the momentum. So the omega is a measure which is often used for angular momentum. And so I said, well, omega is an angular momentum thing. And so that's a natural method we use. But the pi is certainly a square root of the momentum. And well, you see, the angular momentum is really a mixture of omega and pi together, or omega and pi r. But the square root is carried through to that also. So, in a certain sense, I suppose the answer to the question is yes. I mean, there's a square root certainly when you go down to the spinners. Of course, you can write this as vector structure without doing it that way. But that's. But if you want to simulate it, I mean, I think you've got a point. Yes, well, that's usually what happens with this. Yes.
So, when you were doing the pre-quantization of the light ray space,
yes.
I was wondering if I got into this, what I need to do with the full geometric quantization.
Yes.
I need to introduce the polarization.
In a certain sense, that's right, but it's not only a canonical thing. You see, the sort of thing is, if you take a space-like surface, you can make, I think, a genuine polarization. But then when you move, and if there is conformal curvature, then your polarization will change. So you don't want a global polarization. So that's why I say pre-quantization. But you're right, the polarization is sort of hanging in the background, but it's not globally defined. And you want something where maybe in one patch or the other you have a polarization, and polarizations don't necessarily agree, or that sort of thing. Yes.
And just one last question. In what circumstances do contact structures emerge in this situation, in Twistor? Because you mentioned the symplectic and the contact space.
Yes, when you have a symplectic potential, that means you just take a PDX thing. Or you want to, again, the contact structure is an odd dimensional space with light rays, for example. So that is a contact structure. That's the terminology right on the front. That means something with a D on it.
No, but I mean,
it's for an odd dimensional space.
The light ray space was 6-dimensional, right?
Well, the light ray space is 5-dimensional.
5-dimensional.
Yes.
So that has a
That has a contact structure.
Oh,
Yes. You have a contact structure already there, so you put the momentum in to make it symplectic.
You show at some moment the non-commutative twistors which appear to describe the completely classical space-time. Whether we can understand this, that there were some little perturbations of this classical space-time as a classical background quantized, or you described the exact quantum background of the classical space-time.
Yes, well, I guess, as I was saying, I mean, the motivation here is to first look at the classical space-time. Now, as far as I can see, you're only going to get something quantum with the additional computation rules for those things. If you just stick to the Z-bar computation rules, there's no room for Planck's constant. I mean, there's no room for the Planck length. Planck's constant is 1, you see. So when you say something small perturbation or something, it's got to be...
So they are quantized according to these rules. They are quantized according to these Twistor rules.
Well, yes, I'm not sure what quantized means here, because it's quantized already here, so the twistors are already quantized, even though the space-time isn't. But to make that space-time pick up some quantum features, I think you need the other computation rule.
So there are two equivalent descriptions of classical space-time.
Yeah, but it's ordinary metric. It's metrically equivalent. But I mean, I'm saying what I hope, not what I know. See, I don't know very similar things to what we did in the non-linear graviton, which was the complex anti-self-dual spaces. But now you're forcing it. I like to keep the right light-ray space because one of the reasons is it's very difficult to know what you mean by local. See, if you try to do a patching which is local in some sense, and you've just got the algebras, I get terribly confused by what it's doing. But if you've got the light-ray space and you're not too far away from it, then you do have a notion of locality. And so you can say, well, I mean by little patch. What I mean by patching little patches together. But there isn't any quantum geometry in this. You might imagine doing quantum mechanics in the background, which was a classical space-time. If that quantum mechanics is to tie in with the geometry, which of course we want, if you make any advances in understanding how gravity interrelates with quantum mechanics, yes, we've certainly got to have that. This is a preliminary program of simply trying to express classical space-times in this framework. You have to proceed beyond that, and sure, to do interesting physics, we're going to have to proceed beyond that. This is probably not going to do any interesting physics at this level.
Well, thank you. Maybe you are going to be victim of some other questions on the coffee.
Okay.
May I have a question?
Thank you. The main role is being played by holomorphy here, right? And that's the main point. Now, when you consider that you go to non-commutative algebras, the class of holomorphic functions becomes extremely restricted. Say, for example, in quaternions or in Clifford algebras.
And don't mean that. If it became that restricted, no, it wouldn't work.
It would work, yes.
Yes.
So
what I mean is that you have a notion, an appropriate notion, which may be of a holomorphic non-commutative geometry. Now, I'm sure Ernesto knows what that means, but I'm not quite sure. A holomorphic non-commutative geometry. And that's got the kind of flexibility on the one hand and rigidity on the other. There's something magical about ordinary complex analysis where you have, and I've always been amazed by it, you have some kind of great flexibility, but when you've got enough globality in some way, it suddenly becomes very rigid. And this kind of feature to the system, I feel, is very attractive from the point of view of trying to describe physics. Now, I want to retain that kind of feature. So you want to have something which has as much local freedom in the sense that holomorphic functions have. But yet, when you have enough globality, suddenly it gets you very rigid, with maybe a finite dimensional freedom or something like that. And that's the kind of picture that I would hope that we can obtain in this kind of description.
Thank you.
Yeah.
The current status of Twistor theory with respect to applications in other areas of physics. For example, string theories.
Yes. Well, this is just, I mean, I thought, of course, was not concerned with that.
Yes,
but with regard to current activity within Twistor theory, it's very much in such areas. You see, whenever it was, in the early 2000s, a written wrote a paper in which he showed how ideas of Twistor theory could be combined with those of string theory, and this sort of launched a new way of looking at high energy physics. I should make the point there that it's always been pretty clear to me that Twistor theory would have important applications in physics for massless particles. When they've got mass, there's a whole area of understanding which I haven't talked about yet. I talked about the Goodley problem, which is to do with the self-dual and anti-self-dual parts, which is still talking about massless things, massless interactions. I didn't actually much about interactions, but the interactions are also contained in these pictures that I'm talking about. So you do have that, but you're only talking about massless things. Now, in these new developments, people get away with it because they're thinking of very, very high energies. So you're thinking of maybe what the gluon background is in LHC or something like that. And apparently these calculations are very important because if you want to see effects which are new physics, you have to know what the old physics gives you. And what the old physics gives you involved lots and lots of complicated calculations. And these calculations are intended to be done with Feynman diagrams in a conventional way, and they can happen in multiple books of computer calculations, you see. Whereas with these new techniques, starting with what Whitman and what some other people preceding with have been able to do, is these formulas, obviously they actually are very simple formulae, and you could obtain them by much simpler methods. Now, bringing the string ideas together with twistor ideas was a powerful way of doing this. It's continued in directions which don't necessarily involve string theory. They tend to involve supersymmetry, but they shouldn't necessarily involve these. I can't talk about it much in detail because I've never buried myself in it. Let me mention one thing which is very satisfying for me. One of my early graduate students was Andrew Hodges, well known today because of the Turing book, which this film was based on, I'm not sure. Anyway, the book gave a lot of insights into Turing's life and so on, which he wrote before he did his PhD work when he came to work as a graduate student. Now, as a graduate student, as a postgraduate student, as a postdoc student, he developed the idea of twistor quantum field theory and looking at diagrams and developing twistor diagrams from Feynman diagrams without very much interest in the physics community. But then when Whitman wrote his paper, then suddenly they were all interested in this, and Hodges' work has become very important in that area. So this is, I feel really gratified by this, after all the work we've done almost single-handed. But it's obviously important, this stuff, and it's clearly made big headway, and in particular in technical achievements, what you can actually do with much simpler procedures than going through these horrendous multiple Feynman diagram approaches. So that's nice to see. It doesn't, as far as I can see, address any of the questions I was talking today. I mean, you can do things like say trying to do gravity theory. You see, you could do the non-linear graviton construction I had here, or the left-handed graviton, and then you could turn away from left-handed by putting in motivations here, which is fine, and that's the thing to do. But again, it's perturbative at some stage. So all these techniques are fundamentally perturbative. And if you want to see whether non-linear features give you interesting geometry, as I do, it's hard to see where it's going. I mean, it's important to do. Certainly if you want to calculate things, it's important. But I'm not sure how much insight it gives you into some geometric questions. But I hope we can get further on these stuff.
Okay, we have to stop here the question session. Let's thank Professor Penrose again.
Bueno, queremos clausurar formalmente las conferencias Lefschetz, no sin antes agradecer a Miguel Jicotencato por su apoyo financiero, a Hugo Campeán por su apoyo financiero también, al director del proyecto Abacus Isidro Hitler por ayudar con las finanzas, al Instituto Politécnico Nacional y a Francisco Torbiates que también aportaron cantidades importantes, así como a la dirección del Cinvestav, José Mustre, Ricardo Pérez, entre todos hicieron cochinito, ¿verdad? Y se pagó el evento. Entonces, bueno, quisiera que agradeciéramos a todos ellos su generoso apoyo financiero. Y bueno, clausuramos las conferencias Lefschetz 2015, los esperamos en un año en las conferencias Lefschetz 2016. Y ahora, muy ordenadamente, lo de la firma de libros, vamos a caminar nosotros lentamente hacia el café, y allá se ve que ya estuvieron en fila, en una fila muy ordenada para la firma de libros. Muchísimas gracias.
Ya.
Se sale.
También le están firmando ahí artículos y así. Yo estoy firmando.
Ahorita que estamos hablando de ese descenso en un planeta, tiene que ser un medio para que sí.